room in the front. I don't bite, don't worry.
Okay, welcome back, everyone. We are jumping back in with some more awesome content, and we're continuing with architecture stuff. We have Natan Silnitsky from Israel up next. Natan is a backend infra engineer at Wix.com. He is on the data streaming team in charge of building event-driven libraries and tools on top of Kafka. He has many years of experience as a developer of large-scale web services, and his passions include clean code, dev velocity, and great software design. So let's hear lessons learned from working with 2,000 event-driven microservices. Natan, stage is yours.
Thank you, Thea. Just let everyone settle in. There are 3 seats here. Three more seats here. 1 more seat there on my left. 1 more seat here if anyone wants. Okay. Okay, so moving to microservices architecture is not that simple. Moving to event-driven microservices architecture is a lot more challenging. So welcome everyone. My name is Natan Silnitsky and I'm a backend infrastructure team lead at Wix. And for the last 4 years, I've developed messaging and event streaming infrastructure for Wix's microservices. And today I want to share with you the story of adoption of event-driven architecture by Wix's more than 2,300 microservices, and the reasons we did it for better handling of growth, of scale, and for handling better resiliency and fault tolerance, but also a lot of challenges and issues that we faced, and the lessons that we learned along the way. So first, a few words about Wix. So Wix is a website building platform which is very powerful for any level of skill, and you can build your online presence but also manage your business online, from stuff like managing and booking your schedule for your Pilates yoga studio, all the way to drop shipping to third-party sophisticated tools. And Wix has more than 100 million websites around the world, which is roughly 6% of all the websites in the world. And around 1 billion visitors come to the platform each month, which translates to more than 500 billion HTTP transactions every day and more than 70 billion Kafka messages. And like I said, we have quite an extensive amount of microservices in production, which change all the time, more than 600 changes every day. So this really means that we needed to find a good architecture to handle this growing scale, this growing complexity of our distributed system. So we did see a huge increase in adoption of event-driven architecture. And like I said, you can have better handling of your growing scale, better recovery from faults and errors. But we did run into quite a lot of issues. So we had challenges in areas like producing message failures, which actually meant we had data consistency issues between different services databases, processing out of order and duplicate events, which caused also a lot of havoc and dissatisfied customers. Sending large payloads. So we had growing use cases, and now we started hitting edge cases like just having a payload that's too big for our message broker to handle, and how what we did with that. So for all of these challenges and issues, we did find solutions, and we gained more and more adoption by Wix developers. And then they needed to get their heads wrapped around the complexity of the production system with all the events running around from one service to another, and understand why bottlenecks are happening and gaps between consumers and producers, and debug and fix stuff. So that's the fourth major issue that we need to deal with, how to make it easier for developers, to have it done in a more self-service way, and having the tools in place. So I will talk about all of these and how we actually managed to fix those and the lessons that we learned from them. But first, let's talk about what does it mean to have event-driven architecture. If we look at the possibilities for service-to-service communication, basically we have either client-server, request-reply, or doing event-driven. And I'm going to use an e-com example pretty much for the remainder of the talk. So here we have our cart service that manages different products the shoppers put into the cart. And it needs to interact with the catalog service because it needs to know the current description and prices for the products, and the user service in order to know which user is currently working on which cart, and maybe they went and come back and still want to add stuff to their cart. And of course, inventory service, because they need to know, maybe I need to tell the customer that we're out of stock, so it won't stay in the cart anymore. So all of these have to be interacted with to gain the knowledge, gain the data. So if we will look at request-reply model, we'll interact with HTTP or RPC, of course, but we can easily run into scaling issues here. First of all, we've moved to microservices architecture, so we have our database that is encapsulated. It's hidden behind the microservice API, and we did that in order to avoid direct access from all the microservices to the same database. Shared mutable state database, it's really an anti-pattern because it will be really difficult to change stuff. Okay, so it's hidden, and we're accessing it via the API. But then, like with the cart service, it needs to request from a lot of services different things. So it won't be able to do like a database query and join all at once. It will need to fetch the information one by one, and that could be slow. And also, one of the databases may have load issues because a lot of services are interested in what's happening there in that particular data set. So okay, we can fix that. We can introduce a cache. So the cart service will have a cache of the data from the other services. But of course, caching introduces its own complexity, one of the hardest things to do in software engineering. And we may end up with stale values and unsatisfied customers as well. Another issue here is the premise that a network is unreliable, right? So we may end up failing to have a request, or maybe it will be stuck. And we can also end up with cascading failures, where we started off somewhere, but then we request something from one service and it requests from another, and a chain of requests. And all the way down, there's some error. Okay, so now we need to propagate there all the way back up, and maybe it's no longer even relevant for the user, the amount of time that has passed. So we need to define good timeouts here, right? And also, if there's increasing load, we don't want to stop service for everyone in case of errors. So maybe we'll introduce circuit breakers to avoid that. So you have a lot of ad hoc solutions. It's really hard to get good reliability set up in a standard global way in your distributed system of hundreds of thousands of microservices when you deal with HTTP or RPC, because each service is a little bit different. And yeah, it's pretty challenging. So if we look and compare this to event-driven architecture, so we see here that the responsibilities have actually flipped. Before that, we saw the CRUD service requesting information from the catalog service. Now, the catalog service is producing events. For instance, product updated topic produces to that events to that topic. Specifically at Wix, we're using Kafka. And then we get the CRUD service consumer that can consume these events. Now, if you notice, I put a red mark here. They are completely decoupled. They are oblivious to the existence of one another, meaning that if there's some momentary issue with the CRUD service, some failure, it's kind of stuck or something, it won't affect the catalog service at all. It can keep on producing, and so the issue is localized and not spread out among all of the data center. And once the CRUD service resumes operation, it can go back to where it stopped. So at least with Kafka, you can guarantee that you will never lose any message. So as long as you don't commit the message because you finished processing, you will always come back to the first message that you haven't finished processing yet. So we never lose anything. Of course, that introduces new issues that I will talk about later on about, okay, we have double processing and stuff like that, but that I'll touch in a bit. But you do see the power of event-driven architecture. So the story I'm about to tell of what happened at Wix, this is like a clarification slide. Of course, we did a lot of things in parallel, but I show everything in a linear fashion, so it'll make it more clear. And also, the issues that we ran into were in multiple products everywhere around Wix, but I decided to keep showing the e-commerce product, so it'll be simpler to follow. Good. So now that we're clear about that, we can start the story. So in 2016, roughly that year, we really started looking seriously at using event-driven architecture. So we had a lot of services starting to feel how does it go. And at first it was quite nice. It looked promising, but the issues did come quite fast. For instance, for the e-commerce cart service database, the data did not reflect the actual catalog. So it seemed like prices were incorrectly shown on the cart. That's a big problem. You don't want customers being annoyed by paying the amount they didn't think they're going to need to pay. So after investigating, we actually saw that sometimes the catalog service was failing to produce messages to Kafka. So we got the update to the catalog service database, but publishing the event failed. And then, of course, the cart service won't update its own database with the updated prices. So the challenge here is what to do when sometimes you get failures to produce messages. And the more deep knowledge here is that we need to make database updates and event publishing be atomic, so they have to happen in the same transaction. Either both the database update and the event sent happen at the same time, or none should happen at all, theoretically. So what we decided to do here is to try and avoid getting these failures. So we wrapped the Kafka producer in a resilient producer, and if there's some issue that causes failure to produce to Kafka, then okay, so we instead produced the messages to S3, to AWS Object Store, and then we had our healer service on the side that periodically polls S3 and wants to get new messages that were unsuccessfully sent, and then it sends it by itself. Yeah, it worked pretty good for us, and we actually built a set of features in order to help developers with event-driven architecture. So it's a library which later evolved into also a service for other technological stacks, and we called it Greyhound. And we also open sourced part of it later on. So the basic premise is that we still have Greyhound producer, Greyhound consumer on top of the Kafka SDKs, and they offer abstraction layer and also a lot of features. So we talked about the resilient producer, but also a resilient consumer. So consumer retry strategies, because sometimes you fail processing and you want to say, okay, I want to process it later on, and in which kind of strategy, exponential backoff and stuff like that. But also not only about resiliency, which is very important, also performance. So we knew that we want to have as easy as parallel consumption as possible in each of the Kubernetes pods. We wanted to gain fast processing. So we also did a parallel consumption out of the box. And for use cases where it was relevant, we also introduced batch consumers, because if you handle messages in batches, then of course you'll get much higher throughput. And also other features that I'll maybe touch on later on. Good. So in 2018, Greyhound was already up and running, a resilient producer, a resilient consumer, and yeah, developers started getting more confidence in using an event-driven architecture, because even if something goes wrong, you still have a method to make it right again. But the resilient producer started having causing its own issues. So we produced to S3, and well, maybe you can think about what kind of issue can happen here. Basically, out of order processing happens. So if the catalog service puts out an event that the e-commerce store owner decides to introduce a discount to one of the products, but then they say, oh no, it's way too soon, it's not Black Friday yet, so he removes the discount, and okay, that should work, right? But for some reason, introduced discount failed originally to be produced, and then the CRUD service will actually get those out of order. So we needed to have a method in place to fix out of order processing, also duplicate processing, which I will touch on later on. Otherwise, we'll get data corruption and really dissatisfied customers. So the basic premise to solve the out of order execution problem is to introduce an ID, a version, a revision ID we call it. So it is attached to each of the entities, the business domain entities that are part of the events. So in this case, we're talking about the product catalog. So we have the product entity, and it is attached a version. So each product has a version. And then it is, the event includes this version, and it is part of the schema of the database table of the CRUD service. So the CRUD service will actually keep the current version in its database. And then if it actually gets events out of order, first it will get event with version 11, then it will process it because 11 is higher than 9. And then when it will get to version 10, it will actually discard it because it's an older version, and you don't really need to process it because you got new information first. Now this can only work if you have everything you need in the entity as part of the event, so you just update your database and forget about any older updates. Now there is an alternative here in order to avoid out of order producing, and that's using Debugging. So Debugging is a product that's connected to a database and actually listens to the database commit log. So databases put down each change that happens into the database in a file, and that's really helpful for backing up data from databases, tables, and also for replicating databases between different regions is also done via this commit log. And what Debugging does is actually perform the CDC pattern, change data capture, It captures changes in database and publishes them to the message broker. In our case, it's Kafka, but they also have for RabbitMQ and others. So Debugging actually takes care of making sure that the events they publish are always in the same order that the database updates will happen. So they take care of the needed atomicity between the database and the event publishing. But at Wix, we currently decided not to use it universally, because the Debugging events are pretty low level, so you get changes that happen in the database. And we work at Wix with higher level abstractions usually in our events schemas. So what will be needed here is to translate the Debugging style event to the business schema event. So it's another hop of translation, consume, produce, and it's a lot more throughput. So it's a costlier solution to actually put in globally. So we use Debugging mostly for migrating databases, but not for event streaming, because we saw that our resilient producer gives such higher guarantees that we almost never see the produce failures, and we have a solution in place for out of order processing. And actually, it's not like only produce side can cause out of order processing. It can also happen on the consumer side. So having a good pattern in place here gets us cover from all around the event streaming topology, and we get a cheaper solution. So that's good as well. Now, adoption keeps increasing and new issues surface. So in this case, the inventory database, the data there does not reflect the actual inventory. So we have our actual inventory, physical inventory, but in our system, the inventory is actually less than what we have. So we lose potential customers, and so it's really unfortunate, especially as Black Friday is coming up soon, to lose a lot of customers. We don't want that. So after investigating, we understood that the issue happened because of duplicate processing by the inventory service. So we get the payment service, the order service saying, order is complete, payment went through, and then inventory service is happy to reduce the inventory so other customers will get an up-to-date picture. But the inventory service doesn't only update its database, it also sends notifications to maybe the delivery service or other things it needs to do. And in that area, in the consumer handling, there was some failure. So we have the ground resilient consumer, it will retry. Okay, now it's retrying, it's again updating the database. It's actually decrementing the amount of items twice, from 9 to 8 and then from 9 to 7. So it's really not item potent. It's changing the state for the same event twice. So what do we do here? Well, quite similarly to the revision ID, we also introduce some identification here, but instead of it being attached to the entity itself of the product or the order, it's actually attached to the event, to the technical event here. So we got an event from the payment service, and it has a transaction ID, and then we update it. Again, it's part of the schema of the database that we, in the inventory service, we put the transaction ID as part of the schema. And then it's really easy if for some reason we get an extra update query to the database, then we just disregard it because it happens on the same transaction ID. So we can keep it idempotent and deduplicate it and keep it safe this way. Great, so 2019, a lot more adoption and a lot of schema level changes in our services in order to be able to support event-driven architecture better. By the way, also for request reply, some of these things are also useful because you can get multiple requests in some scenarios as well. So now that we have a lot of adoption, more edge cases are propping up. For instance, one thing we needed to handle is just payloads that get too big for Kafka. And in this case, it looked like really weird because all the event has is a product description or product descriptions, which doesn't seem to be too big. But when you get more usage and more customers, you start getting more edge cases, and descriptions can be quite long. So here it actually went bigger than the default in Kafka, which is 1 megabyte. So you can increase the default in Kafka to be bigger. But where does it end, really? If you increase it too much, then Kafka can be much slower because you get a lot more big payloads coming out throughout the brokers, which can really slow down things and really hurt performance. So that's something that we decided not to do. Instead, the first thing we did is introduce compression globally. And actually introducing compression also helped with performance because the payloads for everything almost everything gets smaller, so you get potentially higher throughput. And the compression algorithm, so we have a default compression algorithm, but also allow to have other compressions if one requires that they're not the default, because for some payloads, different compressions work better. And also it was important to note for us that compressing on the Kafka level is much better than doing compression on the application level of the payload, because with Kafka, we noticed that it can compress multiple events, multiple messages in one batch, which is, of course, much more efficient. Now, even after introducing compression, still you can have payloads bigger than the amount allowed. So another possible solution is to do chunking. So we split the original message into chunks and produce each one separately. And then the CRUD service consumer needs to consume it, and actually it needs to keep state. It needs to know, okay, which of the chunks have already arrived, and then once everyone arrives and it keeps it somehow, it needs to reassemble it, and then you have the original message and you can actually use it and process it. So this is quite a lot more complex than actually is usually required. While we have such code that does this for developers, they usually don't choose it because it adds more latency, and it's quite a complex solution. It's not out of the box at all. A more popular approach is to just put the bigger payloads in S3 or some other object store, and then you have a reference to the payload in S3, and that's what you publish in the event. Also for large domain events that you publish in events, you can keep those in a database and not put them as part of the event, and then just produce a reference ID for the domain event. And then later, the consumer can download the object from S3 or go and request the payload from an external service if that's necessary. Cool, so 2020, we added compression by default. We're handling a lot of edge cases. And like I mentioned before, this is a time where really the adoption is exploding. And we're starting to run into an issue where, like, we're a small infrastructure team, and developers really starting to get frustrated. Well, okay, we moved to event-driven, and events are really nice, but I'm completely blind to what's going on, and how do I debug? How do I investigate? How do I fix things? It's really unnatural to me, and I don't know what to do here. Especially troublesome is when a lag builds up, there's a gap between consumers and producers, and you need to close it as quickly as possible. On the one hand, you don't get like a hard failure, but you do have a limited amount of time until you need to close that gap again. So for instance, one of the things that kept coming back is we want to know what's inside the Kafka messages for different topics at different times. And since we introduced encryption for security, it really made it harder for them to do it by themselves. So we decided that we're going to create a back office, a Kafka control plane that will serve and give a lot of tools for developers. There are a lot of open source solutions for this as well, but for us, we wanted to have a custom solution that fits our requirements perfectly. So the first screen is a simple stream of messages. So you choose the topic that you want to stream, the region, a data center that you're interested in, and then you filter it according to some time stamp or according to a partition, a topic, and also, of course, according to all kinds of keywords that you're interested in the payload or the header. And then you can really pinpoint the messages that you care about, and of course it decrypts them and handles the security for you. Cool. So like I said, another really critical, really scary thing for developers is a growing lag between consumers and producers. And what we did here is that we created a screen where they can see the breakdown of the lag for each of the partitions. And not only that, they can also click on some specific, they can even click on some specific partition and see the first message that is not committed yet. So in this case, it may give a hint as to why the consumer is stuck and is slow and is not processing the message. Maybe it's related to this payload. And another thing that kept coming back is something didn't happen that should have happened. Well, you know, everything is asynchronous, everything is running, and some side effect didn't happen. So we have a consumer, it updates some database. No, it didn't update the database. Why? We needed to put infrastructure in place to make it easy to track the events flow throughout the system. So we introduced in Kafka headers via Greyhound, the request ID, the original request coming in from the user, and the user ID, and we propagate it through Greyhound. So the producer writes it to Kafka headers, and the consumer reads them, and then makes it available for the monitoring infrastructure, and then reproduces them again, so it propagates throughout the system. And because we put it in files that the monitoring system then can scrape and put into the monitoring dashboards, we can actually see in Grafana, specifically at Wix, all the artifacts that were part of the flow of the services. And not only that, we actually use the OpenTelemetry protocol so that we write more information for each event. And with the OpenTelemetry protocol, we can actually see how long it took for each processing to take place in each of the services, and the breakdown, how long it took for updating database or calling RPC and stuff like that, and gain more insights. Now, so we worked on it for the last couple of years. Most of what you saw now is about debugging, and more recently, we're working on tools to actually fix issues. So for instance, easily skipping and replaying messages in cases that you maybe there's some event that had bad schema or something like that. Just today I saw in Slack that it was used to great satisfaction of a Wix developer. And also we had an incident last Black Friday on where there was a lag on specific partition because they chose a distribution key which was incorrect. So you know, Black Friday, everyone is really stressed, and all the messages come to a single partition, so that means sequential processing. And they ended up needing to change the key and oh no, they removed the key and GA'd the service. So what we set up now for the upcoming Black Friday is to, in a few clicks of a button, be able to redistribute all of the messages into all of the partitions, so that we can easily fix the lag here. We may end up with out-of-order processing, but at least they will be processed and transactions will happen. Great. So to summarize, Wix developers have really warmly embraced event-driven architecture. There were a lot of hardships along the way, but as we met the challenges and we put the tools in place, we got an architecture that is more decoupled, resilient, scalable, and with the solutions in place, we also kept the complexity relatively low, and of course a lot more consistent than what it would have been without the tools, because if you don't have the tooling in place, it will be a lot more challenging to have wide adoption. So if you want to get more details on each of the pitfalls, the challenges, this talk is based on my blog post, and I have all the slides on SlideShare, so you just need to remember one link, or basically my name. And if some of you here actually working with Kafka and starting to get really high traffic, so in Devox UK earlier this year, I gave a talk on strategies to split up into multiple clusters, because your scale is growing in a lot of different parameters, and also how we migrated our clusters to a managed Kafka environment on the cloud, specifically Confluent Cloud, and that really helped us focus on the tools that I mentioned, and not cluster optimizations and rebalancing and stuff like that can be left for the experts in our case. And if you're interested in more information on the Greyhound features, there's extensive documentation you can find on GitHub. And tomorrow I'm giving a talk. It's the first time I'm giving a soft skill talk on creating tiny habits to become a better developer, all based on this book by James Clear. So if you're interested in pursuing changes to your habits, you're more than welcome tomorrow. And thank you very much. So thank you. So you can find all the slides on SlideShare. You can also check out my website, natansil.com, where you will find a lot of blog posts I've written and previous talks I gave in conferences. And follow me on Twitter and LinkedIn, everything about Kafka, event-driven architecture, and software engineering in general.
Anyone has any questions? There we go. I knew there's going to be some. I've seen some people taking notes. Okay, you were first, I believe.
Yeah, thanks for the talk. Very interesting.
Thank you.
So the architecture, like in the end now, looks quite complex, right? So you have to do some workarounds and all. And of course, like once you start into this, right, it's harder to go back. So it's better to keep going forward. But now you have tooling and everything in place. But if someone has to solve a similar problem today, what would be your recommendation? Like still going with this, or maybe there are some better ways to do it?
Okay, so it's not like we completely got rid of RPC in our microservices. So developer always has the choice to go the RPC route. But Wix is really evolving into our goal of an open platform. So everything a developer exposes has to also be exposed to developers on top of the Wix platform. So you have Wix developers that are your users, you have external developers that are your users, and sometimes you would want to have a procedure call, and sometimes you want to emit an event. I won't say that events are the holy grail for everything. It's always trade-offs, and you have the tools in place, so just choose the right tool for the job. Basically, I hope I answered your question. Sure.
There was one more here, yeah?
So you developed this Greyhound, and so it's dealing with the messages and so. So for example, when you have some, I think it's yeah, sorry. So I think when, for example, you have a message that is stuck and you cannot process, do you have any tooling like to get that message, to investigate, to modify it, because that message is not longer being able to? And if you have tons of these messages, what is your strategy to deal with, I don't know, thousands of them, because you cannot manually?
Okay, good question. So basically, if you have a bad message, you cannot actually modify it. In Kafka, Kafka is commit log immutable. Yeah, so you cannot modify it, but with your consumers, you can actually change the index of where the consumer is currently found. It's not like with the queue that you're removing a message from the queue, using it and discarding it. You actually just have an index, an offset, that like a pointer throughout the partition. So, like I mentioned, we introduced tooling to easily skip messages or replay messages, like going back and forth. It used to be a lot harder, but as you make it easier, then you can say, okay, it's a few bad messages, I'll skip it. And in Kafka, it really doesn't matter if it's 1,000 or 1,000,000, because you just change a pointer. So it's really easy.
Yeah, no, my question was more focused, like, how do you solve this problem? Because you have a distributed event with some microservices expecting some state, and one microservice didn't. So you could skip that message for that consumer, but then this consumer would not have this state. So you will probably have to consume this message, change it to a good message, and then publish it again somehow only for this consumer, or how do you deal with that?
Okay, so you're saying that you have a bad message, but there's still useful data there. So in that case, I guess one option is to change your consumer code to actually be able to process it even with the bad schema, and redeploy and replay the messages. That's one option. Another is to request new events from the original database or stuff like that. But that will be interaction with the topic owner. But basically, you're talking about something that can happen a lot, about schema changes, version changes. It can happen a lot. But as long as you have the ability to change your code and to replay messages, you're a much better position than in the request-reply world, in my opinion.
Okay, and we have one more question online. Tim is asking.
You can contact me later. Yeah.
Yeah, of course. You can all contact Natan later as well. Tim is asking, if compression speeds of Kafka, why don't they do it natively?
Why isn't it turned on by default?
I believe so.
Well, it's a good question. I guess I guess it does introduce a little bit of latency, and if you have hugely high critical infrastructure, then where each nanosecond is important, which Kafka does have a lot of those use cases, then it won't be a good default, and you could have, I don't know, encrypted data where you cannot compress it, because compressing encrypted data only expands the data, doesn't shrink it. So I guess it depends, and that's why it's not the default.
There you go, Tim. We hope we answer your question. And this is it for our time with Natan, but you can definitely ask him online on Pine. You can message him directly. And of course, there's a party tonight where you can just buy him a drink.
I'll stay outside
exactly.
as well.
Okay, so that is all. And we have a longer break now, and we'll see each other in an hour.
So I'll stay here if we have a longer break.
Yeah.
Thank you.